Discharge, flux, and velocity are three words that we use all the time in geomorphology. Reason for that is because they describe material moving. So for example, velocity might be the easiest to think of. And so if I'm looking at this image right here, at this canoe might have a velocity where it's being pulled down the river in that direction. And the canoe is going to have a single velocity unless, something terrible is happening, right? Because if the front of the canoe is going faster than the rear of the canoe, then that's usually the start of a very bad day on the water. The water itself, speaking of, also has a velocity, and its velocity profile might be different. It might have something like, slow velocities over there, and then faster velocities farther from shore, and getting even faster towards the center of the river. And so I'm just going to draw this arrow to be even bigger and fatter. We're not going to talk today about the sort of variations in velocity that we see across rivers. We're just going to pretend that right now we have equal velocity everywhere. Or just really ignore that entirely, because we're dealing with more of the mathematical concepts than its actual implementation in geomorphology. There's one more term on the right. So we've talked so far about discharge here and velocity here, but there's also this thing called flux. And there's also something called discharge per unit width, which is also given this small q character. We're going to talk about those a little bit more in the next several slides. One thing I want to just show you, though, before we completely bypass this image, because I think it's important to train our eyes as geomorphologists, is that this is a very, very flat cliff face, right? Super, super flat. And then you see this material that's all down here along the shore. It's all fallen off, right? So what we're actually seeing is landslides and landslide deposits. And we can also represent this as a discharge or a flux. It's really common to talk about discharges and fluxes of water, but we can do that with this hill slip material. We can do this with the sediment that's moving along on the bar. And we can do it with this other hill slip material that's creeping over here. And in fact, we can even say that there is some sort of, if we had enough humans going across the river, we could actually talk about the discharge of humans across some particular river cross section right here and say, oh, look, we are discharging, one canoe per 5 seconds. So discharge and flux are really important terms because they describe mass and volume transport, and in fact the transport of lots and lots of different things. So discharge is the rate of movement of some parcel of material. So we could have mass discharge, we could have volume discharge, for example. And the flux is the rate at which that same parcel of matter, so something like water or sediment, energy, or anything else, for example, some kind of chemical constituent, is crossing a surface at a single point. And for that, we'll need to know something about the geometry of the surface, and we'll need to know something about the orientation of that surface with respect to the vector that's describing the discharge. So fluxes could be things like, again, water. They could be sediment. It could be, vegetation, or it could be something like, Marty McFly in a time-traveling DeLorean. But regardless of what we're thinking about with flux, the reason that we're thinking about discharge and flux is that we're going to combine them with some conservation rules to understand how the shape of the landscape changes. Conveniently, rocks and, by extension, sand, gravel, mud, most of this stuff, is not super compressible. Mud a little bit more so, but we're going to focus mostly on larger classic materials, so sand and gravel and so forth. And if that material is mostly incompressible, then we can actually think about this whole process in terms of conservation of volume. And therefore, I'm going to think about volumetric discharge to avoid the need for unit conversions via a density. At surface conditions, water is almost perfectly incompressible, so that works also. And I'm not really using units in this lecture, but I am using dimensions. So there aren't meters or feet or anything. There's always just going to be length and time. But in general, I'm going to use the SI units as much as possible. So meters, kilometers, kilograms, seconds. Well, meters, kilograms, seconds, kilometers being kind of an extension in the metric system. So moving on from that, we have discharge, and so this discharge is related to this volume on the left, this cube, and the cube has units of length cubed, right? So a length that is right over here, times the length that's right here, times the length here. Those three, if multiplied together, are going to give you the volume. And this time term comes in because we're actually thinking about how this cube is translating through time, and at some point it's going to hit this imaginary plane. That plane could be describing the cross-section of a river, or it could be anything else. And we want to know how when it passes through that plane, what component of that flow is going to be normal to each individual point on this plane. So if I move forward, we have discharge here, which is given by this big Q, and we have the smaller q over on the right, which I call flux. And that flux has units of length over time. And that might seem, kind of odd, kind of interesting perhaps, where this other length squared go. Well, the thing is that what we do is we look at the discharge at going through every single point here, and then we project it up. And then we project it. I wonder what just happened. Pen width, normal. Mouse pointer is pen. There we go. And then we just project it normal to that plane, and that creates our flux relationship. Sorry about this. My tablet's actually just causing us to keep flipping slides, but at least it keeps it a little more exciting. So what matters here is both the area of this plane that we're projecting into this volume moving across, and its angle with respect to the orientation of the discharge. So right over here. And if we assume that discharge is just one single value, and we basically just have it's related to some uniform mean velocity, but doesn't even have to be mean, but is uniform through the whole system, then we can just make it a lot simpler and say that the flux is related to the discharge divided by some sort of area. So now we can move on to the next slide. So here we are. So we have this area of the plane here. We have this unit vector that's normal to the plane over here. And so it's how much of this is going through this plane, knowing that this unit vector, which is supposed to be directly opposite to this, is pointing in a direction that's a little bit different than this arrow. And by the way, we're using Q for flux here, but we're going to use it for something that's a bit different, and I'm going to define that in the last slide. And by that, I mean it's something that's a bit different when working through the rest of the class. All right, so let's relate discharge and flux. And the deal here is to use the dot product. So if you're not familiar with the dot product, go online, Google it. You're going to find it out. But basically, this thing on the right here where I just add this cosine of the angle alpha, that's your answer. So going back to the left. So we have flux is equal to discharge over area. So this is some sort of normalized discharge. And it's dotted with this normal vector. And so what that means is that we actually care about the angle between these two different planes. And that'll determine how much and how efficient this discharge is at crossing that plane. So if the discharge is going across a plane like this, it'll be pretty efficient. Over like this, it's going to be a little less efficient because this material keeps on going this way, but we really want to know what's going off in that direction for the flux. And then it's multiplied by the normal vector again, because we need to actually have this flux be a vector quantity, so it needs an orientation. So here we are. If we want to think about in trigonometric functions, we can create a plane defined by the vector space of this discharge and the flux, with the flux being in the same orientation as n hat. And after defining the space, we then just find the angle between the two of them, looking in the same direction, this angle alpha. Then we can take cosine alpha to do the exact same thing as the dot product right over there. So here's a quick thought exercise that's related to geomorphology. So I have a river left bank and a river right bank, and we adopt the river rafters convention for what we call left and right. The left bank of a river is the bank that's on your left-hand side if you're floating downstream. The right bank of a river is on your right-hand side if you're floating downstream. If the river is not flowing, then it is really not a river. And That actually creates a little bit of confusion, especially in northern Minnesota, where there's so many swampy flat zones where there are rivers connecting lakes, but the rivers and lakes definitions are actually a little bit more fluid in that landscape that's been carved by glaciers as opposed to being created by river systems. But we'll table that for the moment, get back to it later. What we're going to do is assume a rectangular channel cross-section, by which I mean that we have some sort of cross-section here with a water height like h and a width b. Oh, that's going off the board. B, which is the breadth in the English language, not in the American English language. But since I mentioned at the beginning that we often use W as a coordinate for velocity, we need a different letter. So we have B. And then we have U bar, which is the mean velocity. And we assume that this channel is rectangular. So think about this for a second. What is the magnitude of this flux? So think about over here, this is going in here. There's going to be some angle. In this case, it's going to be a right angle that this is going into this plane at. But what we really want to know is how it compares to the normal to this plane. And it is parallel to that normal. And so what we end up getting is that this discharge, this little q, is just equal to big Q over width times depth. And the reason for that is because if you think about this, we're taking cosine of an angle of 0 degrees. Cos 0 is 1. Or you can also just think about the fact that this guy is moving perfectly perpendicularly to this plane, and so it's going to be the most efficient at moving material past that plane. Second thought experiment. What if the plane were like this? Now this is going to describe, there's the answer. This tablet needs a little bit of calibration. So this is going to describe material moving across this plane that's right in the middle of the river, and so that's going to tell us, is there anything moving in what we often call the y direction? So crossing the middle of the river. And that's important for thinking about things like turbulence, or if there's a velocity that's higher on one side than on the other side of the river. But here we're dealing with just a single uniform velocity moving as what we call a plug flow straight down the channel. And therefore, we don't actually have any velocity that's capable of crossing this. You can also think about the fact that we are dealing with here, there's a normal and hat, and that's a 90-degree angle, and cos of 90 degrees is equal to 0. And therefore, there we go. That's the answer. I gave it away early, but the flux here is 0. Hopefully that makes sense. So, you might be wondering why we're introducing this different word flux, because we have this other word called velocity that seems to describe the exact same thing we're talking about, right? It has the same dimensions. It's also a vector quantity. It's also describing something moving, so are they the same thing? And the answer is actually it depends on how you define that surface that they're crossing. So on the left-hand side in that figure, if we're just dealing with the situations that we had in the past several examples, yes, velocity is flux. So for example, in the first one where I'd have little q of flux equals big Q of discharge divided by width times depth. Here, I'm just going to take some space to write this down. So big Q is equal to, scratch that out, little q is equal to big Q over width times depth for this rectangular channel. This is also going to be equal to u, which is the velocity. However, if we take this middle case here, we have this piece of the surface that's going through that black thing, which is representing a hard, impassable object. And so over here, u equals 0. And so over here, therefore, u has to be greater than q over bh, because b is defined as this whole width of the channel, right? And so you need to have extra speed to make up for that lost speed in the middle in order to maintain continuity, so in order to maintain the same amount of flow going through that channel as the discharge is dictating. On the right-hand side, you've actually just redefined that surface to no longer include the obstruction, and then once again the discharge and the velocity are the same. So here's the key. The answer is sometimes. However, and very importantly, in geomorphology, these things are typically identical. In something like if you're studying groundwater, you might deal with some of these obstructions in the middle all the time in ways that you can't actually observe or measure directly. Things like when working with flow through porous media, you might be able to know what the area of some wall of an aquifer is, but you don't actually know from direct observation, unless you have a lot of cores, where every single sand grain is. And even if you have a lot of cores, you haven't observed every sand grain. And so what you have to do is figure out, based on some porosity, the relationship between the flux of material and the velocity. So those are different. In geomorphology, we have these convenient things called river channels. And if we describe the river channel properly, then we're only describing the geometry of the zone where water is capable of flowing, and velocity and flux become the same thing. Therefore, this little q starts to become a little bit useless. And so we decide to redefine it as something that's a lot more useful. And so when we're working to understand things like material moving along a hill slope or down a river valley, so here's my little hill, and then here's my river with a free water surface and some flow down this way, I'm not mapping out this y dimension, this cross-channel or cross-hill slope dimension. I'm just mapping out the dimensions that are changing, right? So I'm going down the slope and down the direction of transport. And this is a really useful approximation. But the thing is that we actually have to then, if we're going to use this, take this big Q and divide it by width, so we're actually getting discharge per unit width. And so now this ends up having units of length squared per time. And that is not a flux. That is not mathematically a flux. However, this is very regularly by geomorphologists and in the literature called a flux, despite its disagreement with the mathematical definition. In this class, we're going to be really careful and use these terms properly, but I need to tell you this because it's so common. So there you go. Here's your mathematical background with a little bit of geomorphological and open channel flow commentary on top of it. We have discharge per unit width, discharge, velocity, and flux. 4 important terms to know as we go through and start to develop more process-based understanding of the geomorphic system.